Today we'll discuss about waves, the physics of propagation. From ripple to symphony, enter an exploration of how waves transfer energy and information through the universe. That I am going to discuss today with you and you see how it works. Now discuss these things, how it is going to work, that I am going to discuss that how the physics of propagation from ripple to that of from ripple to symphony, an exploration of how wave transfer energy and information through the universe. See, waves transfer energy, not matter. A wave is a propagating disturbance. The particles of the medium oscillate around their equilibrium positions but do not travel along with the wave. These patterns, which move without the actual physical transfer or flow of matter as a whole, are called waves. You can see here, this is analogy water, this is analogy sound. If you put some cork pieces on the disturbed surface, it is seen the cork pieces move up and down but do not move away from the center of disturbance. Particles oscillate locally. But in case of sound, when you speak, the sound moves outward from us without any flow of air from one part of the medium to another. Particle travels with the flow. This is the difference between these two, water and sound. Now you see here, a wave's character is defined by the direction of its dance. Transverse waves and longitudinal waves. Constituents of the medium oscillate perpendicular to the direction of wave propagation. They create shearing strain and can be propagated in media that can sustain shearing stress like solids. You see here, this is the particle oscillation. This is the wave propagation. Therefore, the angle between the particle oscillation and wave propagation is 90 degree, and this is known as transverse wave. Longitudinal waves, constituents of the medium oscillate parallel to the direction of wave propagation. They create compression and rarefactions and can be propagated in all elastic media, solids, liquids and gases. You see, the particle oscillate here. The wave also goes in this direction, and this is compressions, this is rarefactions. The distance between two compressions or the distance between two rarefactions, the wavelength or lambda, you can say the lambda. Now you can see here the decoding the blueprint of a traveling wave. Decoding the blueprint of a traveling wave. Single function of position x and time t can be described the displacement of every point in the medium at every moment. Displacement of a particle at position x and time t can be described as y xt is equal to a sine kx minus omega t plus phi. When this is amplitude, the maximum displacement from the equilibrium position, the peak of the mountain, that is a. K, angular wave number, represents how tightly a wave is coiled in space, 2 pi times the number of waves per unit length. This is what we call as the phase. Phase determines the state of oscillations at any point in space time. This is angular frequency, omega, represents how rapidly the wave oscillates in time. An initial phase angle, the phase at x equal to 0 and t is equal to 0. And how it sees how the displacement occurs. This is displacement, this is position, this is just a wave. And this wave is represented by yxt is equal to a sine kx minus omega t plus phi. Wavelength defines the wave in space. Period defines it in time. Snapshot in space, fixed t. Video of a point, fixed x. This is wavelength, lambda, see, wavelength and period. Wavelength lambda, the minimum distance between 2 points having the same phase. It is determined by the wave number lambda equal to 2 pi by k, or k equal to 2 pi by lambda by 2 pi. Period. The time it takes for an element to complete one full oscillation is determined by the angular frequency t equal to 2 pi by omega. Frequency. The number of oscillations per second is known as frequency. Nu equal to 1 by t, omega by 2 pi measured in hertz. These are the few definitions or factors we define in wave, that is wavelength, period, frequency. And these are one of the most important definitions of these wavelength, period and frequency. The wave's speed is a property of the medium, not the source. This is displacement, this is position. In one period, a wave travels a distance of exactly one wavelength, v equal to nu lambda or n lambda, you can say, omega by k. The medium determines the speed. For a fixed speed, velocity v, higher frequency nu from the source results in a shorter wavelength lambda and vice versa. Then v equal to n into lambda or nu into lambda. This is velocity, this is nu, that is omega by k. We'll find this one. Wave speed on a string, a tug of war between restoring force and inertia. The speed of a mechanical wave is determined by the ratio of the medium's elastic restoring properties to its internal properties. Tension. The restoring force that pulls displaced elements back to equilibrium. Higher tension equal to faster snap back is equal to faster wave. Linear mass density, mu, the mass per unit length that resists acceleration. Higher density equal to more sluggish, more slower wave. And v is represented root over t by mu in case of string. The speed of sound depends on how easily a medium is squeezed and how heavy it is. Elastic property. The bulk must be a measure of resistance to compression. A stiffer medium, high B, propagates waves faster. Inertial property. The volume density, rho. A denser medium is more sluggish and propagates waves slower. General formula, B is equal to root over B by rho. B is the bulk modulus and rho is the density. The Newton's Laplace correction. The Newton's initial model for gases is equal to root over P by rho, assumed constant temperature. Laplace correctly identified the process as adiabatic, no heat transfer, leading to the accurate formula P equal to root over gamma P by rho. You can see here the comparative speed of sound in various media. This is medium, gases, air, liquids, water, solid, steel. You can see here that the velocity in solid is greater than velocity in liquids and velocity in liquids is greater than velocity of gases. Because solids are much stiffer, higher B than they are dense. So you can see here in case of steel it is 5941 meter per second, and in case of liquid it is 1482, in case of air 331. Comparative speed of sound in various media. You can see the speed of sound in various media. In steel you can find 5941, in case of water it is 1482 at 20 degrees centigrade, and at 0 degrees centigrade the speed of sound is 331 meter per second. So you can see that the speed of sound is greater than the speed of liquid, and the speed of liquid is greater than that of the speed of gases. Waves don't collide, they coexist and combine. The principle of superposition. When two or more waves overlap, the resultant displacement is the algebraic sum of the displacement due to each pulse. They pass through each other completely unchanged. This is the approach. Overlap the displacements and algebraically. This is the continuation. The rule yxt is equal to y1 xt plus y2 xt. Interference, power of phase. When two identical harmonic waves overlap, the outcome depends entirely on their phase difference. Constructive interface. Phase difference phi is equal to 0. Crests align with crest. The waves are in phase and the resultant amplitudes doubled. Waves you can see here. This is the phase, same phase, and it will be doubled. Destructive interface. Phase interference phi equal to phi equal to pi. Crests align with troughs. Crests align with troughs. The waves are out of phase and the resultant amplitude is 0. You can see here, this is the phase and this is pi difference. Therefore, y plus y2, the resultant amplitude will be 0. This is the power of phase, or this is what you call it as interference. The wave's reflection depends on the boundary it strikes. Rigid boundary, open boundary. Here say the rigid boundary, that is fixed end. This is the fixed end you can see here. The wave reflects with its phase inverted. A phase change of pi or 180 degree. An upward pulse reflects as a downward pulse. Open boundary, that is a free end. The wave reflects with no phase change. An upward pulse reflects as an upward pulse reflects as an upward pulse. Phase change is 0. Here phase change is pi. Here phase change is 0 if it is an open boundary. Standing waves. The stationary dance of interference. You see, we find here nodes and antinodes. Nodes means 0 displacements. Antinodes maximum displacement. Maximum displacement is antinode, formed by the superposition of an incident wave and its reflection, creating a pattern that does not travel. The amplitude varies in space to a sine kx, while the whole pattern oscillates in time cos omega t. Yxt is equal to 2a sine kx cos omega t. Normal modes, the natural harmony of an object. When a system is constrained by boundaries like a string fixed at both ends, only standing waves that fit perfectly can persist. These are its normal modes of oscillations. You see, it is fundamentals, second harmonic, third harmonic. Constraining formulas, boundary conditions, capital L equal n, lambda by 2 for n equal to 1, 2, 3. Allowed frequencies, nu equal to n, nu by 2L. The combination of the fundamental frequency pitch and its harmonics timbre is what gives an instrument its unique sound. Here you can see that it is lambda by 2. This is lambda and this is 3 lambda by 2. Right? This is fundamental frequency when n equal to 1. Second harmonic n equal to 2. First overtone n equal to 3. That is the second overtone. Right? This is the what we call when the system is constrained by boundaries like a string fixed at both ends, only standing waves that fit perfectly can persist. These are its normal modes of oscillation. Beats, the pulsing rhythm of interference. When two sound waves of close but not equal frequencies nu1 and nu2 superpose, the interference is alternatively constructive and destructive, creating a periodic variation in amplitude, a beat. See, this is the wave 1, nu1 equal to 11 Hz, wave 2, nu2 equal to 9 Hz. Resultant wave, beat frequency nu1 minus nu2, that is 2 Hz. Beat frequency is nu1 minus nu2. Application, this is how musicians tune instruments by ear. They adjust the pitch until the audible beats disappear, indicating the frequencies are identical. From a single sine wave, a universe of complexity emerges. Waves are propagating disturbances that transfer energy governed by a medium's elastic and inertial properties. A simple mathematical function y equal to a sine kx minus omega t provides a complete language to describe them. A wave's speed is dictated by the properties of its medium. The simple rule of superposition unlocks complex and beautiful phenomena like interference, standing waves, and resonance. These principles are the foundation of sound, music, light, and modern communications, demonstrating how a few fundamental rules can build a symphony of complexity. Thank you everybody for watching this video.